Hello, everybody, and welcome to Lesson 3, Quantitative Data Analytics. So this is where I really think near-infrared calibration starts getting really interesting. If you think about the first couple of lessons, we laid a groundwork. We discussed the principles of spectroscopy. And then our lesson 2 was talking about instrument design. So what we've done on the instrumentation side to gather the right data. So now we're going to start exploring what we can do with that data, and specifically some of the mathematical and analytical techniques that we use to evaluate those data. So let's jump into this next lecture. All right. So lesson 3, quantitative data analytics. So this is an outline, and you will see in this lesson that I will mix some of the terms, some of the mathematical terms. They will have multiple names for them. And this is just a warning, but this is introducing some statistical and mathematical techniques. And sometimes we will fall back on historical names for some of these mathematical terms. So, an example here is, the objective here is model making. So this is the outline of what we're going to go through with this lesson. So we will go into model making. We will talk about the structure of the data and what the different parameters are involved. We will talk about evaluating and making a relationship between these different parameters that are involved. What exactly is an under exactly or overdetermined system as far as these different parameters go? Talk a little bit about the concept of complexity and how that relates to our data set. Look at feature selection as one way of dealing with this complexity, and specifically how it relates to multiple linear regression. We will then look at feature mapping and factor methods, or feature extraction methods. And we will talk about the source table and the loading tables, otherwise known as eigenvalues and eigenvectors. And finally, talk a little bit about how we can use these measurements also to give us some assurance or confidence in the measurements we're making through outlier determinations, and that's through the Mahalanobis distance. So if we jump into data analysis, this is just pulled from Wikipedia, but data analysis is the process of inspecting, cleansing, transforming, and modeling data. So really, that's what we're going to be doing with our data sets. And I really like the next part. It says, with the goal of discovering useful information, supporting conclusions, and supporting decision-making. Really, that's at the heart of what we're doing. This is a very common part of our life right now, with the access to almost unlimited amounts of data, and we hear the term big data all the time, incredibly fast computers. Data analytics are a huge part of our life. So we've got just some examples up here. One of the ones I think about is the loyalty cards and all of our personas that we've got online. Not only what does it give us, but how is it used and how is it sold? And what kind of information are people mining from our everyday life activities? So that's a pretty good example of data analytics as it's being used in our lives today. There are many names for data analytics out there: machine learning, AI, artificial intelligence, data mining. These are all kind of different flavors of data analytics. Become very, very popular in the last 15 years or so, 20 years. And really, spectroscopy relates in there. So at the end of this, whenever we're going into data analytics, we have to have a concrete way of expressing and listing and describing our data. And in most cases, the data comes in the form of tables or grids that are filled with our data. And this is put into some sort of a form, some sort of a database, some sort of a mathematical structure that then we can work on with our different algorithms. So the rows represent examples, and the columns will contain some sort of an identifier, some sort of a true response or something we're relating to, and then one or more feature measurements. And the feature measurements are measurements that we've made that hopefully we're going to be using to create this relationship. And normally the objective is to derive a model that will predict a response value from a given set of feature measurements. So in our case, the feature measurements, for example, are the raw data, the spectra, or the absorbances at the various wavelengths for a given sample. And what we're eventually trying to do is to predict a response, okay? And this would be a constituent value. So we'll see this table a couple of times. And really, this is how I think of the structure of the data that we are working with. So we talked about this and we said that various rows are the examples. So these are the samples that we've been analyzing on our instrument. We've got columns for responses, and these are our constituents of interest. In this example, we've got moisture, ash, and protein, and these would be reference values from a laboratory. So we've sent these samples out to a reference lab, and we've obtained these reference values, responses. And then the features are all of the absorbance values at each wavelength that we've collected for these samples. So in this example, it starts at 1350 nanometers, it go up to 22, 24, 2600 nanometers. So you can imagine that on the feature part of this table that we've got hundreds and hundreds of columns that contain all of these absorbance values. This is a really good example of what our data really look like. So in the background, what we're doing is we're working with linear algebra. And at the beginning of this course, I told you that I'm not a chemometrician or a statistician, but I'd like to describe this in a way that you know, I've been able to work with it through the last 20 or 30 years. And linear algebra is just a way that uses tables to create relationships and solve and generate models. And there are quite a few different software programs that are out there that will do this. Very common ones, well-known ones are MATLAB, R, SAS. When I first started, my first company used SAS quite a bit. R is a free version that's out there. These statistical packages will really do a lot of what we're doing with UCAL4. They just do it in a very generic, more manual form. And one of the things we've tried to do with UCAL4 was, again, to put it into the hands and to put it into a form where it was very intuitive to use for an IR enthusiast. Okay. And Microsoft Excel even has many of these matrix functions. So for the mathematical wizards that are out there, or people that just have a genuine interest in this, you can actually go in and do some of these processes, some of these calculations in Excel. UCAL4 does this for you, thank goodness. So here's a quick example. If we just go back to the most basics of algebra, if we've got this linear, this equation, so 7 equals 5 times a constant, 3 times a constant. We've got two unknowns, B1 and B2. Can we solve this? And we can't. We've got one equation, one example, but we've got two unknowns. So this is not a solvable question for us. If we expand this a little bit, and we now have two equations, can we solve for B1 and B2? And the answer is we can. And if we remember back to algebra, we can create an equation which will express B1 as it relates to B2, and then substitute that into our second equation, and we can solve for this answer. If we expand this a little bit, now we've got three equations. Can we solve for B1 and B2? And the answer is yes. Now we just have an additional equation which will support our investigation, which will support our ability to solve for B1 and then B2, or vice versa. So in mathematical terms, what we have here are different equation sets. And when we had one equation and two unknowns, we had an underdetermined system. And in an underdetermined system, we are not presented with enough information to solve the problem. When we had two linked or related equations and two unknowns, we had an exactly determined system. So again, we could create an equation that expressed one of the variables in terms of the other one, substitute that equation in the second, that equation, and solve. So in this case, we've got an exactly determined system, and this is one we can work with and one we can solve. When we had three equations and two unknowns, it just expanded on that. We had multiple ways that we could relate these variables to each other and then solve it. So this is called an overdetermined system. And we've got many solutions, many ways, many paths to create this solution in an overdetermined system. To do useful modeling, we'll need to be working with overdetermined systems. So that's something to keep in mind. So the number of features should be less than the number of samples. The number of spectral features, in our case, should be less than the number of samples. Okay. And for those of you that are keeping track, these are the solutions for the two different sets of solvable equations that I presented. So if we make the jump from algebra to linear algebra, we can convert this into table equations. And again, I'm not going to get into this. I'm not a linear algebra genius, but we're doing the same thing. We're taking the feature values, we're taking the spectra, we're creating a link, the coefficients, and we are predicting out the response values. We're just doing it rather than in a simple equation, we're doing it in a matrix. And again, this table. So we are relating these data. So if we take these data, you can actually do this in Excel. And you can go through and you can create these relationships. And there are linear equations that you can calculate in Excel and come up with a coefficient and actually a model in Excel. This is very manual, but if somebody's interested in looking and investigating the math behind it, there is a way that you can go into Excel and actually make these calculations on very simple matrices. So if we step back a second, and if we think about the problem that we're starting with and the problem that we're trying to solve, typically with our instruments, with a SpectraStar, we've got over 1,000 features. So remember, the features are wavelengths. So if we think about our rule that we needed fewer examples or fewer features than examples to be able to have an overdetermined system, how many samples would we need? If we've got 1,000 features, we're going to need more than 1,000 samples. And that, just imagine, we all look at near infrared, and one of the things we're trying to do is we're trying to develop an analytical system. And number one, have very timely, robust, reliable information. But we're also, in general, trying to cut down on the number of samples that we're sending to an external lab. We're trying to manage our analytical costs. If we always needed to start with over 1,000 samples, that would just be a huge hindrance to creating near-infrared calibrations. So this is a lot of samples, and it would just be a huge burden to even get started. So how can we deal with this? Well, this is just one of the reasons why we do this, but what we can do is we can make an underdetermined system into an overdetermined system. So if we think about the scale and the dimensions of the data that we've collected, the number of samples or examples versus the number of wavelengths, and this is our matrix, what we can do is we can simplify this or reduce it so that the number of wavelengths that we're looking at or wavelength-related data are smaller than our examples. And that will turn this into an overdetermined system. Okay, so the matrix starts looking like this and the dimensions are solvable. There are two different strategies that have been used over time, and they kind of progress historically. And if you remember one of the first couple of lessons, I think I mentioned that the rise of near infrared as a routine tool really paralleled the ability or the rise of personal computers. And you'll see that with some of the calculations that are necessary going forward, that we need strong computers to do it. Historically, there are two different strategies to reduce our data set. One is to reduce the number of wavelengths, and the other one is to compress the data in the wavelength space so that we've got a more workable system and really converting it into a factor system. So let's start with the first one. First one is feature selection. Well, this is both, I'm sorry, feature selection and feature extraction. So these are the two different methods that have been historically used. The first one that came out was feature selection. And this is basically looking at your data set and trying to determine the most important features and modeling on those features only. So this is a selection. The newer trick is feature extraction. And this is converting or reducing the data into a higher dimensional space, a mathematical space with a much lower dimension than the original wavelength, the individual wavelength matrix. So we are mathematically reducing our wavelength space into a much smaller high dimension feature space. Feature extraction is the key to modern data analytics, especially those big data applications. And I think in our examples coming up, you will see why. It has some real key capabilities that make it unique and make it very useful for what we're trying to do. Feature selection still has a place in certain areas where the number of examples is small or where you need to keep the number of examples small. So let's look at feature selection. There are three different methods that have been historically used. Again, the first one is to just brute force looking at all combination search. So if you think about that, we've got over 1,000, let's just make it 1,000 different wavelengths. If you started iteratively going through that matrix, picking the first wavelength, trying to look at the other 999 and figuring out which was the next one, and then iterating again down and finding the next one, and then restarting the entire process with wavelength 2, that would be an all combination search. It would be possible to program, but it would take forever. The next method historically that's used is step up. And step up is where you find the best feature or wavelength in our case, and you grab that one and you find that feature usually based on a correlation. And once you've selected that first one, you've got a base, and now you look at the remaining data and you find the second best, and then the third. And at some point you determine when to stop. Okay, that's step up. The other one is step down, and it's the opposite. So what you're trying to do is find the features that do not help you, that show no relationship to your constituent or parameter of interest. So you get rid of the worst features and you whittle this down until you've got a small number of features that are the best ones. I think in most cases, step up is used. We do have the ability to do MLR calibrations. They're really not used very often with scanning monochromator technology. But it is used, for example, it can be used to translate information from a scanning instrument into a filter instrument. So step up would be a way that you could determine the best filters to then put into a filter instrument, for example, for an online or process application where scanning monochromator would not be appropriate. Okay, so that's still an algorithm that is used. One caveat here, watch out for overfitting. You've got very limited data and you're picking your features very, very carefully. If you pick too many wavelengths, a lot of times you're pushing the math beyond its ability to explain this larger feature set. So you need to be careful about overfitting. Feature selection is the best method when sample acquisition is difficult. So for whatever reason, you've got a very limited ability to acquire calibration samples. Feature selection is very good because you've got only a couple of wavelength features that you can explain the variance. So you don't need that many samples to do it. On the opposite side, feature selection is not very robust. So it can't explain or can't handle much sample variation. If you've only got a couple of features or a couple of wavelengths to explain your sample variation, there's not a lot of variation that you can explain. So in general, these are the pros and cons of feature selections. Your models usually have a limited application. Again, you can't explain that much. Many models are needed when products have a wide range of constituent values or if they're changing a lot. And you need to test and validate your models to make sure that you are sticking within the original parameters. On the pros, products with predictable ranges work very well. So if you're in a production environment, for example, and all of your samples fall into a fairly narrow, repeatable range, feature selection can work very well. And one of the biggest pros is a very reasonable model can be made with very few samples, sometimes as low as 5 samples. So feature selection is definitely a way that you can deal with an overdetermined system. The more widely used is feature extraction. For feature extraction, what we're doing is we're using factor methods to map or translate the entire feature set into a small set of score values. So now we're starting to use some data analytics terms, and you will see some terms used interchangeably with this. The way that I think about feature extraction is we're doing a mathematical reduction of an incredibly complex matrix, and we're bringing it into a smaller data set that was selected very deliberately to optimize the variability that we had in the original set. Okay, there are two different factor methods that are widely used that we use. The first one is principal components, our PCA, principal component analysis. This is useful, especially when you've got features or wavelengths only. In this, with a PCA method, we are looking at your spectral variation only, and we are mathematically reducing it. We also use partial least squares, PLS, and this is a response-weighted method that takes into consideration also the variability in your constituent values. So PCA can be used even when response values, constituent values are not known, but PLS does require constituent values. And again, one of the caveats we talk about is beware of overfitting. Beware of pushing the math too far and chasing relationships that are really not valid in real life. We'll talk more about that. So as I was saying earlier, I think of feature extraction or these scores methods as a way to mathematically reduce your data or compress your data. Feature extraction was an early method of data compression starting in the 70s. It looks like it was used for determining orbits and related information about interplanetary satellites. If the eigenvectors or loadings or principal components are available, scores can be produced from the original data. So this is getting to how we use these data compression techniques. So first we determine a scale, a vector to measure all of our samples, and that's an eigenvector or loading. And once we've determined that, we can produce scores or eigenvalues for every single sample based on that system, that mathematical system that we've set up. So we can, once we've got that system, we can produce the scores from the original calibration data. The original data can also be reconstituted from the product and scores in the eigenvector table. So we can actually reverse this process. And again, I've got an example that will hopefully try to clarify this. But you can actually do the mathematical reduction, take your 1,000 data points, for example, your 1,000 wavelengths, reduce it down into a smaller feature set, and then mathematically reverse it and bring it back out very close to the original data set. So whenever you go into a mathematical reduction and then you reverse it, when you bring it back out, you lose some information. The resolution, the fidelity is not perfect, but you can bring back most of it, and we'll discuss that. In our case, it's not unusual for 8 or 10 scores or 8 or 10 principal components to accurately map over 1,000 absorbance columns. This really illustrates, that we've got some redundant and some information in the spectra that is not useful for what we're doing. So feature extraction or principal component analysis is a way that we can zero in on the spectral information that does help us predict our constituent of interest. After we've got the 8 or 10 scores or factors, the remaining scores map noise that we're just tracking irrelevant or uncorrelated noise or information in the trading set. It's not helping us at all. So this is a very efficient way of zeroing in on the information that is useful to us. So this is quite a data reduction. So how many samples would be needed to achieve an overdetermined system if we had 10 features instead of 1,000? And I'm hoping everybody knows that it would just be more than 10. This is a pretty simplified illustration, but it shows how well data compression and looking at these mathematical reduction techniques can take an unsolvable and massive data matrix and bring it down into a reasonable level, a reasonable scale that then we can use for calibration purposes. When I started in near infrared, I had multiple really smart people try to explain principal components in data reduction to me. And on the second or third explanation, I think it started to take hold. If you asked me to generate a principal component analysis from scratch, I could not, but I've gained a very functional and usable knowledge of it. This is one of the ways that I think about doing some of these feature extractions or principal component analysis. Imagine that you're given this problem. You've got this huge pile of bananas, and you need to develop a system that characterizes and identifies and describes each one. And the goal is to relate these simplified measurements and look at, this new system of characterizing all of the bananas. You want to relate that to sweetness. Let's say that's your constituent or parameter of interest. So how would you go about describing and characterizing these bananas? Conceptually, you could use a principal component analysis or a feature extraction. And in this, you're going to select the characteristics in the order of explaining the most variation. Thus, you want to pull out the feature that describes the most variation. And once you pull out that variance, whatever's left, whatever variance is left, then you want to find the feature that explains the next greatest amount of variance. So for bananas, it might look like this. The first principal component might be length. So if we just look at this, and if we make a measurement from end to end of the banana, that would be our eigenvector or our loading. So that is our measurement that we're making. Once we determine that that is our first principal component, our first characteristic, every single sample in this pile could be rated based on that measurement. And if we rate and separate each one of those samples in the original pile based on length, we might be able to describe 87.3% of variance. And I just made this example up. Our first principal component did a great job of looking at this huge pile of bananas and characterizing and identifying the individuals. But we still have some variance that is left over. We've still got some redundancy. In other words, we've still got quite a few bananas that have the exact same length. So we need another measurement. We need another vector. We need another principal component to go in and characterize these bananas. Our next one might be circumference. In this, let's say we look around the middle of the banana, we measure the circumference, and we characterize all of the bananas based on circumference. We discover that we've described another 6.2 additional % of variance. Out of the remaining variance that we have in this big pile, this redundancy that we still need to explain, we might look at the median color. And let's say we've got a Hunter color measurement. And we look at the LAB and we find out that the B value in an LAB color measurement, the B value correlates the most to the residual variance. And we can explain an additional 3.9% of variance. Weight, another 1.9 of the remaining variance. And the curvature offset, let's say we draw a line between the ends and we can measure this. And for some reason, this has got the next highest amount of variance to explain. Well, with these 5 measurements, with these 5 loadings or eigenvectors, we can explain 91% of the variance. So very quickly, we've made 5 measurements that look at this entire pile of bananas And we could pretty well characterize every single one in that pile. If you think about it, however, we haven't thought at all about our original goal here, which was to create some sort of a model for sweetness. And we'll talk about that a little bit different. But the point I want to make here is that the principal components describe the bananas themselves, okay? And they're providing a system that we can very uniquely score each banana with 5 different measurements, and we can then relate that to whatever property of interest that we're looking at. Okay, so that's how I think of principal components. I've had other explanations. I hope that helps you. The real key parts here of principal components is to understand that we are making selections and we are trying to explain variance. And what we are going to try to explain with our systems is the variance that we're finding in the near-infrared spectrum. So one caveat here is beware of the overfitted model. An overfitted model is a model that does a great job at predicting a training set, but it performs very poorly or unexpectedly in real life. And the key to optimum fitting is to understand complexity and where it's coming from. Okay, usually complexity is proportional to the number of features. And you just saw that we reduced our features from over 1,000, for example, with our near-infrared spectra to 10 or so eigenvectors. So we're reducing the number of features. If we're looking at polynomial math, it is generally the order of the equation. So the exponents. The exponents add complexity. If we are looking at feature selection, that was the first method we looked at. It is the number of wavelengths that we're selecting. So the complexity is proportional to the number of wavelengths we choose. If we're looking at feature extraction, it is the number of scores or factors or terms that we're pulling out. Okay. The more scores, the more eigenvectors that we are using to describe our samples and creating the eigenvalues for each sample, the more we use, the more complexity that we are adding to our system. How do we determine when we're approaching a danger zone? So if we're underfitted, we know that the training set members and a test set do not predict well. In other words, I'm going to put these in terms that I use to understand it. If we're underfitting our system, we are not investigating to a detail, to a level needed. We are not extracting the information we need from our system to generate accurate data. If we are overfitting, an independent test set will predict unreliably or poorly, while the training set will look great. So we've pushed the math, we are tracking information that does not relate to real life, and we're fooling ourselves into thinking that we've got this fantastic calibration. That's an overfitted calibration. It's very dangerous. We want to avoid this. So how do we deal with this? We can evaluate this with a press type plot. And if we look at a press plot, on the x-axis, we are increasing our measure of complexity. And on the y-axis, we're looking at some sort of an error measurement. And press plot will show a characteristic shape, as we will see, and it helps us determine where our optimum complexity level is. So general strategies to avoid overfitting. Use your training set to compute the parameters. So that's, for most of what we're doing, we're going to be looking at feature extraction or some sort of a principal component analysis in PLS. Okay, so we're talking about scores and factors. So we will use the training set to compute these parameters. So we will use the training set to set up our principal components, to set up our eigenvectors, and then to compute our eigenvalues for the various samples. We'll then use a test set to set what's called hyperparameters. So these are small little parameters that determine how we are going to evaluate our data. And these include things like math processing that we will do on our spectra, on our information, our raw data coming in. It also looks at the degree of complexity, the number of factors. We will then use a validation set to evaluate the overall results. Cross-validation is a technique which can take the place of a test set. And cross-validation is a very efficient way of evaluating these hyperparameters using your calibration samples while maintaining a degree of independence in this evaluation. And the reason why we do this is if you think about it, we're always trying to optimize or maximize the return that we're getting from our lab resource, our lab budget, the amount of money that we're spending to send our samples out to a reference laboratory. Cross-validation allows us to optimize these hyperparameters while not spending money for an independent test set. So what we're going to do is we're going to optimize our complexity with this cross-validation. And UCal is built around the ability to use cross-validation. Sometimes mathematical circles, it's called multifolds, where they describe the folds as cross-validation groups. During the regression phase, when we're using cross-validation, samples are assigned to a fold, okay? And we go through, this is an iterative process. So we perform multiple regressions with the fold members excluded from the training set. So they become a validation set for each one of these independent regressions. So the resulting model from the included samples is then used to predict the fold members. Okay? In this way, we can use the calibration samples, but also have a degree of independent validation within our regression process. Okay? Thus, each sample in the training set is present once in an excluded case, and it functions as a validation sample. And we can use this to determine the optimum number of factors. So cross-validation is used for us only in PLS, and we call these groups. I don't like the term fold. Again, it's a mathematical term, but we talk about cross-validation groups. We've got different ways of doing grouping. We can do sequential, random, it's random number generator as far as which samples are included in each group. We can do a constant random, which is a pattern or a block. There is a rule for the number of groups that you should use. If the number of calibration samples is greater than 45, you should use 4 or 5 groups just to be efficient. And what this is reflecting is that if you've got more than 45 samples, you've got sufficient samples that you're creating validation groups that are statistically relevant or valid. Okay? If your number of samples is less than 45, well, first of all, you're getting into kind of a dangerous area with PLS. I really don't like to go below 30 samples or so unless I absolutely have to. But if you're under 45 samples, you can use 8 or 9 groups. And this is just so that you are doing enough regressions to get a statistically valid look at these test sets. There is also something in the software called LOO, or leave one out, and you can use this for very small sets. And this will create a number of groups equal to the number of samples that you have. Okay? Computers are so fast that we can afford to do this now. Okay? So this is a diagram of what cross-validation looks like. In this case, we are going to do a 5 cross-validation groups. And the ones in the yellow are the ones that are being part of our validation. So in the first iteration, sample number 1 in the first position would be part of an independent validation. We would make the model on samples 2 through 5, and then we would validate it on 1. And of course, if we've got 200 samples, this would be repeated. So 1, 6, 11, 16, all of those samples would be picked for the test set, and the intervening groups of 4 would be used as the calibration set. Okay, this would be the first iteration in cross-validation. Then there would be a frame shift, and sample in the 2nd position would be picked, sample in the 7th position, sample in the 12th position, and so on. The remaining samples would be used for the calibration set. Again, you do a validation. You sequence through all 5 of these, and you average the results here, and that gives you a very good, cross-validation estimate, a validation estimate of your calibration performance. If you look at this, every single sample was present in an independent validation set, but at the end of the day, the model is created on all of the samples, and all of the samples can be included. So this is a very efficient use of your calibration samples. Well, this is great. So we go through this cross-validation. How do we evaluate it? Well, this is a generic test plot. So we talked about it a couple of slides ago. On the x-axis, we've got some sort of increasing complexity in our feature extraction, or in our PLS, principal and component space. This is the number of factors on the x-axis. We're looking at an error on the y-axis, so a predicted error. Okay. The training samples are in black. The test samples are in blue. And what you will find many times is that your training sample will just continue to show lower and lower errors as you are adding more and more factors. What you are doing is you are following extraneous information in your training set that will not help you in real life, will not help you when you get to your unknowns. So you are overfitting your model. You are tracking variation that does not truly relate to your constituent of interest. And this is where cross-validation comes into play. If you look at your test samples will also decrease in error as you are increasing your level of complexity or your number of factors, but they will reach an optimal point. And after that, you will start overfitting. Your independent test samples will start increasing in error, and the performance will start going down as you start adding factors that are modeling noise, that are chasing noise. So a press plot typically shows this characteristic shape, and what we're looking is for that optimal point in our test samples where our error is as low as possible. And once we get to the calibration phase in UCal4, you will see that this is one of the key plots that we will use to evaluate our calibrations and determine the number of factors to use. Okay. Another thing we can use with feature extraction or with principal components is we can plot these scores. So remember that we described what the system was of evaluating our samples. We discussed eigenvectors or loadings and eigenvalues. So these relate to the axes in this three-dimensional plot. You can see that we've got on this one, on the X, we've got factor 1 or eigenvector 1. We've got 2 on the Y, and then going back on the Z, we've got 3. So this corresponds to the first 3 principal components, or the first 3 loadings that were calculated based on this sample set. Okay. Once we've described the system, once we've described these loadings or these eigenvectors, we can then go into every single sample and we can determine what their scores are and plot them in 3 dimensions. And this 3D score plot is very useful. We're going to see this in our exercises once we get there. One of the things we can see is that we've got, in general, there's 2 clusters. And we'll see in the software that we can rotate and we can zoom in on this. But if you think about it, there's one group of samples here, there's one group of samples here. So that's one of the things quickly a principal component plot can show us. We can see we've got one sample that's way up here. We can look at each individual point and we can determine what its scores are for each one of the loadings. And we can also look at a global distance. We'll talk about that in a little bit. So this is a visual representation of the sample variance in a principal component or a 3D space. Okay. And if you think about it, compared to 10 or so slides back where we had that table, where we saw our features and we saw that we had over 1,000 columns describing our spectra, there's no way that we can evaluate the variance and how our samples relate to each other from a table like that. Well, through feature extraction, through principal component analysis, that same variance is represented here. And it's very easy for us to take a look at this. So 3D scores plot, the amount of information for each sample or by each sample score can be easily computed and plotted. The fraction of the variance that's explained can be calculated. So if we look here at the first principal component or the first factor, it's almost 98% of the variance in this case is being explained. The second one is 1.4. So you can see that for the first 3 factors, we're explaining, in this case, 99% of the variance. So it's extremely efficient at identifying the variability within our sample set. First 3 scores will normally explain over 90% of the information. It's a very useful point, or plot, I'm sorry, and each point is a sample. So that's a visual representation of what we're doing through this feature extraction or this mathematical reduction. We're going to find that it's going to be very useful once we get into our regressions. Okay. A little bit of history quickly. There was a famous Indian mathematician, Mahalanobis. This is also from Wikipedia. And he figured out a way to use distance measurements to classify human skulls. So a way to look at the data, multiple measurements, and classify human skulls. So, and with the Mahalanobis distance, we're working in our mathematically reduced or score space. And we are using a standardized measurement in that space. And we can make 2 different measurements with Mahalanobis distance. We can start out with a global distance, which is the distance from the center, the mathematical center. And we can also do a neighbor distance, which is the distance in principal component space to the sample that is most similar. Why do we want to make these measurements? Well, one of my earlier lessons, if you remember, one of the things that I said about near-infrared is that near-infrared is very good at interpolating, but it's not very good at extrapolating. And very early in near-infrared, there was no real way to determine when you were extrapolating. So you could be extrapolating for a number of different reasons. Your constituent levels could be much higher or much lower than was represented in your calibration set. Or your sample, the raw data, the spectra could look very different than those included in the sample set. In either case, you are extrapolating, and that's a situation you want to avoid with near-infrared spectroscopy. So the global distance and the nearest neighbor distance help us determine spectrally when we are extrapolating. So a high global distance means that your sample probably doesn't belong in the model, and its prediction could be unreliable. It's saying that this sample spectra looks different from those included in our calibration set. A high near neighbor means that your sample has no close neighbors in the training set, and its prediction could be unreliable. So this indicates that you've got a hole. Your sample might belong to the overall group, but you found a hole in this principal component space, and there are no close neighbors. This is generally a very valuable sample, one that's got a low global distance but a high nearest neighbor. This is one that you want to be adding back into your training set. This is a picture that I've done, I don't know how many hundreds of times in various fashions, but this is a very simple representation of what we're doing. If you think about our 3D plot, score plot that we had before, let's simplify it down into 2 dimensions right now, okay? So if we've got 2 different dimensions and we plot all of our calibration samples based on 2 different factors, and these are the scores based on 2 different factors. All of these are our calibration samples. We then analyze an unknown. We evaluate it based on the same loadings or the same eigenvectors, and we find that the scores of this unknown sample are outside of those included in our calibration set. Remember, we said under 5 for a Mahalanobis distance. This unknown sample would be above the limit, and that would be suspect. So this is a way to identify the spectra that were not represented well in our calibration set. So that's our global distance. Our nearest neighbor distance, or neighbor distance, ND, is using the same system, the same coordinates, the same loadings that we have set up. But in this case, we are measuring the distance to our closest neighbor, the closest neighbor in our calibration set. And if this distance is above a limit that we've set, we found an area that belongs in the calibration, but it's a hole. And in general, this would be a great sample then to take, send to our laboratory, get the reference value, and add into our calibration, making our calibration more robust and filling out this spectral space. So this is how we are evaluating and calculating our global distances and neighborhood distances. Okay, a couple more thoughts. The process of feature extraction involves the development or creation of a training set, or we call it a calibration set. So from this calibration set, we find and we create the loadings. These are the eigenvectors. Using this, we can calculate the scores for each sample. So we're mathematically reducing that massive table of individual absorbances at each wavelength into scores. This process is somewhat reversible. If you have the score set and a table of loadings, you can almost completely recalculate or recompute the original spectrum. If you remember, we are explaining percentages of the variance. So some of the variance is lost. If you go into a principal component space and you reverse it and you recompute back out to the full resolution data, you will lose some of your information, but it's a pretty small fraction. So this is an interesting part of mathematical reduction techniques. Principal components are done on spectra only. In PLS, the loadings are weighted based on the constituent values. So with PLS, when we're calculating those loadings based on the calibration set, we are paying attention to the constituent values as well. So principal component analysis yields a table of loadings or eigenvectors. So the rows are the eigenvectors. Table of scores is calculated, and these are the eigenvalues. And these are properties of the training set. There is an algorithm that computes this. If you want information on this, please, go out and look at it. But in theory, there are as many eigenvalues and eigenvectors as there are wavelengths. That's in theory. So if you had 1,000 samples to completely explain this, you would need 1,000 eigenvectors. In reality, there's so much redundancy and the samples are so similar that we use an extremely small fraction of these. So in this slide, it says 99.5%. A huge percentage, a huge majority of these are due to noise or redundancies or information that's only in the training set. So this is really a good filter for finding the information that is useful for us. One of the nicest things about scores is that they're mostly independent of each other. And if you think about my banana example, I think I did length first. I believe I did circumference second. So you can imagine that for bananas, as they're growing, length and circumference might be somewhat related to each other. But we also had color in there. And color could likely, especially the B value for color, could likely be independent of the other measurements that we were making on the banana. For us, when we are searching for variance in our spectra, these scores can be largely independent of each other, but might relate fairly tightly to our constituents of interest. One of the nice things about calculating these scores and working through this system in a decreasing order, explaining more and more variance, is there's very little redundancy in scores. So it gives us an opportunity to find independent and useful information in the data set. The first three scores usually represent a huge majority of the information, but might not be where you need your information for your constituent of interest. The first three scores can be used to plot a sample's relative location. So you're looking at the gross characteristics of the spectra. Every once in a while, you need to sometimes in a 3D plot look at higher order or fourth, fifth, and sixth factors, for example, in your plots to find information that's useful. If two samples have the same or almost the same score values, they are very similar to each other. So this is one of the key aspects to this whole principle of mathematically reducing spectra. If the sample spectra are virtually the same, they better have very similar chemical or constituent properties. They must, or else our system is not going to work. So this principle is saying if these samples are spectrally very, very similar, then it follows that my measurement of interest, my constituent of interest, should be very, very similar. And I only need to represent that sample once. Okay? So we're trying to weed out redundant samples, redundant information that does not help us. Scores can be very useful for grouping samples and for recognizing unusual samples. We will see that about halfway through our exercises. We will start using this to find unique samples and the best samples for calibration. Okay, and we're going to search for the spectra and the features of the spectra that are unique and useful, and we're going to trust that that variance will explain our constituent variance effectively. So quickly, eigen. Eigen is a description. It is German. We've been talking about eigenvalues and eigenvectors. They're characteristic of this matrix, this data matrix. The loading matrix is a partial eigenvector matrix. So the eigenvalues can be calculated from the training set. And this is how it's done. You are not going to use these values directly. This is all done behind the scenes in the software. But it's very important that you understand what the mathematical reduction is doing and where these factors are coming from, because during your process, when you are developing your calibrations, you are going to be evaluating the effectiveness, the performance of your models based on the number of factors that you're using. And if you've got a good understanding of what the factors are doing and how we are investigating, more detailed information through this, the remaining variants that we're explaining, that will help you determine the proper number of factors to use in your model. Okay. So this is really what we do with the software. And this is pretty much the end of the data analytics lesson. We do have a couple of slides here. If we are doing a evaluating complexity, there is another way to evaluate complexity depending on the modeling we're using. We started in the beginning, we talked about feature selection, and we said that the more features, the more wavelengths we select in feature selection, that's increasing complexity. We are doing feature extraction or principal component analysis or PLS. We are adding factors or eigenvectors or loadings, and that's how we are increasing complexity. One small part of the software, we also use polynomials. So quickly, if we are dealing with polynomials, in the area of the software that I've used that uses polynomials is when we're calculating instrument transfer calibrations, okay? But if we look at complexity in a polynomial equation is listed here. So we've got the exponents, 0 order, 1, 2, and up to whatever. The exponents describe the order of our polynomial equation. If we take a data set that looks like this, we can go in and we can actually do this in Excel. We can go in and calculate various polynomial explanations for this data set or polynomial models. And we can determine, make a prediction, make a predictive model based on a polynomial equation. Okay. We can also use a similar system to evaluate the performance of the model, and we can do it based on errors. We can do this in Excel also, and if we look at our coefficients in the orders of the equation that we're making, we can create this out to 6, for example. If we plot them, we can plot the predictions versus our order. We can do the error. This is really similar to a press plot based on our order, okay? And we can see that in fact that we are getting some sort of an optimal order through our polynomials. If we look at a magnified error plot, we can see that it's performed poorly at the ends. But what we can do, which is our true press plot, is we could look at the residual sum of squares values or an error value, and we can plot this against our polynomial. So our training set is decreasing in error as we just start adding more and more terms. Our error goes down, but as we've talked in real life, an overfitted model will fall apart and the errors will increase. And this is very visible in this simple example. We've got the same shape in our press plot. So looking at our validation set here in the red, we can see that the third order polynomial produces the optimal performance on our independent test set. This is just a short explanation for the polynomials. It just follows the same patterns as we do when we're doing factor-based mathematical reductions and factor-based regressions. Again, the only part of the software that we really use higher order equations is in the calibration transfer section or instrument transfer section. But this illustrates that you want to use the lowest order calibration or instrument transfer equation you can, because as you start adding polynomial factors that do not relate to this relationship, your errors can increase very significantly. So that was a quick explanation of data analytics. There are some key parts to this. What I really hope that all of you can take away from this is to understand a feature extraction technique, how we are taking these hundreds and hundreds of data points in an extremely complex mathematical problem, how we are mathematically reducing it, focusing on the areas of the spectra that demonstrate variance. And then we're going to use this mathematical reduced spectra and this demonstrated variance in this system in our regressions going forward to create our NIR calibrations. So thanks to everyone for your attention, and we will move on to our last lesson, which is our next lesson, which is qualitative data analytics. Thank you.